Welcome to today's episode, where we're diving into the fascinating world of distributed systems and how they stack up against single-node systems. As technology rapidly evolves, grasping the core differences and challenges that come with these systems is becoming more crucial than ever. We're going to unpack the complexities of concurrency, explore the nuances of concurrent versus parallel computing, and shine a light on the essential role of consistency models. Along the way, we'll tackle the challenges of maintaining shared state, discuss the importance of fault tolerance, and look at innovative strategies like backpressure and process local queues that can really boost system performance. Let's start by clarifying what we mean when we talk about distributed systems versus single-node systems. In a single-node system, everything is relatively straightforward. Operations on variables follow a predictable sequence because you're working within a single-threaded environment. But once we introduce multiple threads accessing shared variables, things get a bit chaotic. This unpredictability is a major hurdle in distributed systems, where each processor operates independently and communicates through message passing. The real complexity in distributed systems comes from the need for synchronization among various threads. If there's no proper coordination, the outcomes of operations can vary, leading to inconsistencies and potential failures. This unpredictability is something developers must carefully navigate when designing resilient distributed systems. Now, let's shift gears and talk about concurrency and parallelism. You might hear these terms tossed around as if they mean the same thing, but they actually represent different approaches to processing tasks. So, what's the difference? Concurrent operations refer to tasks that overlap in time, meaning multiple processes can make progress without necessarily running at the same moment. On the other hand, parallel operations are all about executing tasks simultaneously across multiple processors. Understanding these distinctions is vital for optimizing system performance. By leveraging concurrency, systems can effectively manage multiple tasks, while adopting parallelism can drastically cut down processing time for compute-heavy operations. As we continue, it's important to highlight the role of consistency models in managing concurrent operations. These models provide a framework to ensure that all processes in a distributed system maintain a coherent view of shared data. They help mitigate the unpredictability of concurrent operations, ensuring that the system behaves reliably. Different consistency models come with their own trade-offs between performance and reliability. Some prioritize speed and may allow for temporary inconsistencies, while others enforce strict consistency, potentially slowing things down. Choosing the right model is crucial for striking the balance between efficiency and reliability. Maintaining a shared state in distributed systems isn't without its challenges. One major concern is keeping all processes in sync, especially when failures occur. As systems scale, the chances of inconsistencies only increase, making robust synchronization strategies essential. Fault tolerance becomes a key aspect of designing resilient distributed systems. By incorporating redundancy and failover mechanisms, developers can create systems that keep running smoothly, even when individual components fail. This resilience is vital for maintaining user trust and ensuring uninterrupted service. As we navigate these complexities, it's also important to be aware of the fallacies of distributed computing. These fallacies serve as cautionary reminders about common assumptions that can lead to pitfalls in system design. For instance, may developers mistakenly assume that the network is reliable, that latency is negligible, or that bandwidth is unlimited. Recognizing these fallacies can empower developers to make better-informed decisions and design systems that are more equipped to handle real-world challenges. Now, let's introduce back pressure, a fascinating strategy for managing message flow within distributed systems. Back pressure acts as a regulator, ensuring that producers don't overwhelm consumers, which allows for smoother processing of messages. By controlling data flow, systems can reduce latency and prevent bottlenecks that could hinder performance. Implementing back pressure requires thoughtful consideration of system architecture and workload characteristics. When done right, it can lead to systems that are not only more efficient, but also more resilient to fluctuations in demand. Next, we'll explore process local queues, which are vital for managing workload in distributed systems. These queues help separate message receipt from processing, allowing systems to handle requests independently without blocking. This non-blocking approach can significantly boost overall efficiency, as it minimizes the chances of failed requests that would otherwise need retries. However, while process local queues can enhance efficiency, they may introduce some additional latency due to the time spent in the queue. So it's crucial to tailor queue sizes to fit the specific workload. For stable tasks, smaller queues might do the trick, but larger queues could be necessary to handle those unpredictable bursts of activity. As we discuss queue management, let's emphasize the importance of sizing queues appropriately. The right queue size can greatly influence system performance and reliability. Smaller queues are often ideal for stable tasks, ensuring quick processing, while larger queues can better accommodate sudden spikes in demand. Even though remote servers can process requests quickly, they can still return failures. This highlights the need for careful response management and the importance of designing systems that can gracefully handle such scenarios. By mastering queue sizing and management, developers can significantly enhance overall system performance and reliability. As we wrap up this episode, we've explored the fundamental differences between distributed systems and single-node systems, delving into the complexities introduced by concurrency and the necessity of synchronization. We've discussed the nuances of concurrent versus parallel computing, the significance of consistency models, and the challenges of maintaining shared state in distributed environments. We've also looked at the fallacies of distributed computing and introduced strategies like back pressure and process local queues to boost system performance. Understanding these concepts and implementing effective management strategies can empower developers to create resilient and efficient distributed systems that meet the demands of modern applications. Thank you for joining us today. We hope this discussion has equipped you with valuable insights into the world of distributed systems. Be sure to tune in for our next episode, where we'll continue to explore the latest trends and challenges in technology.